Alright, welcome to our fourth video in this first unit on functions. And in this video we're going to talk about domain and range. But first, let's do our warm-up for today. We've got 6 problems here that I'd like for you to think about. And when you're ready, move on and we'll talk about them. Alright, so let's talk about number 1 here. We got negative 4 plus 7 minus 3. So negative 4 plus 7. Let's do that first. So you can start at negative 4 on your number line and move 7 to the right. Or you can think of it as, instead of negative 4 plus 7, you can think of it as 7 minus 4. 7 minus 4 is 3, and then minus 3 is 0. Alright, number 2, write all y values greater than 3 as an inequality. So you've worked a little bit with inequalities before. Let's remind you of what that looks like. So y values greater than 3. So y is greater than 3. So the distance between these two endpoints is greater than the distance between these two endpoints. So you can see that so the y is greater than the 3. So it's saying that that side, the quantity on that side is greater than the quantity on this side. If we wanted it to be greater than or equal to, we would do that. So I just wanted to remind you of the inequalities because we're going to be working with those a little bit today. Number 3, is this a function? So like we talked about last session, we want to think about if this is a function or not. And we had to think about, does every input have exactly one output? And so if you go along with the horizontal axis here, you can think about every single one of those inputs. Does every single one of those have exactly one output? So this has an output here, this has an output here, here, this one has one up here, this one here, this one here. Every single one of these inputs has exactly one output. So it is a function. Now this is not a function that we've talked about yet. This is what we call a periodic function. You're not going to really get into those much in integrated 1 at all. But just know that there are functions that are periodic, meaning they repeat over and over and over again. Like this one has waves like that, which model things like sound and other things. So anything that oscillates really up and down can be modeled by that kind of function. So let's go on to number 4 here, 7% of 51. So again, we want to take the two numbers involved minus any trailing zeros, and we can multiply them together. So in this case, we're going to multiply 7 times 51. So a little multiplication strategy here. Let's drop the 1 for a moment and just do 7 times 50. So 7 times 50 really comes down to 7 times 5, which is 35. So 7 times 50 is be 350. And then we're going to add on the last multiple of 7. So 7 times 1 is 7. So we're going to have 357. And just think to yourself, is 357 7% of 51? No way, right? It's too much. Is 35.7 7% of 51? No, that'd actually be 70%, not 7%. So let's keep going. Is 3.57? That makes more sense, doesn't it? Especially because if 7%, percent is per 100, so 7% means 7 out of 100. So if it's 7 out of 100, then it should be about half of that for 50 out of 51. So 3.57 makes sense in terms of the context there, or the problem there. All right, what percent is 1,021 of 4,084? Well, that might have been a little challenging for you, but what's really nice here is if you recognize it, this times 4 gives you this. So if this is 4 times this one, then this makes up a quarter of that value. So therefore, 1,021 is 25%. 25%. I'll go ahead and fill in some of these other answers while I'm thinking about it. This one was 3.57. Okay, last one. Divide 1,234 by 1.234. Again, pretty challenging unless you think about it not as a division problem, but as a multiplication problem. So let me ask you this. Instead of dividing this by this, let's think about it this way. This number times what would give us this number? Let me give you a simpler example. How about 6 divided by 2? Yes, you could think about it as division, how many groups of 2 would go into 6 and that kind of thing, or 6 divided by 2. Or you could think about it as 2 times what gives us 6? 2 times 3 gives us 6, so the quotient would be 3. Well, let's do the same thing here. This times what gives us that? Well, they're actually the same numbers involved, so really it's going to be a product of 10, or a power of 10. So let's see. If we multiply by 10, that's going to be 12.34. If we multiply by 100, that's going to be 123.4. If we multiply by 1,000, we get 1,234. So if we multiply this number by 1,000, we get this number. So therefore, this is 1,000. There's 1,000 of these that go into that. All right? So, with that, let's go ahead and move on to our topic for today, which is this here. Our topic and our goal is to identify the domain and range of a relationship or relation given a table, set of points, or graph. And then we also want to identify the reasonableness of a domain for a context. So given some sort of context, what is a reasonable domain? All right, so we're going to have that as our goal for today. So let's go ahead and talk about domain and range. In our last video, we talked about how domain was going to end up being our input values. But let's go a little bit further here. It says all values that can be inputted. And I put in parentheses x there. Most of the time it's going to be x. Later on in your mathematical career, you may think about something other than x. Also, if you have like a geometric formula, let's say the circumference of a circle, the input then is probably going to be the radius, which is represented by r, not really x. So I put x in parentheses there, but know that it's whatever the input value is. So the domain is all values that can be inputted, and there's a number of things that might keep us from inputting certain values, and it may just be it doesn't make sense in the context, that kind of thing. But it's all values that can be inputted, and the range is all values that can be outputted. So all the values that could possibly be outputted are going to make up our range. And I put y in parentheses there again, and most times it's going to be y, but there are certain situations, going back to that circumference example, if you input the radius, you're going to output the circumference. And so it's not necessarily y that's going to be your output. But we can start by thinking about it as x's and y's. Okay, so we brought up these set of points in our last session, and now we want to talk about the domain. So remember, this one was not a function last session because 5 outputted 2 different values, and because of that, it's not a function. But we can still think about our domain and our range. So our domain is made up of all the input values. So if we think about that in set notation, so you can use like a little curly brace here. Set notation, we're going to list these out. 3, 5, 7, 8. We already wrote 5, so we don't really need to write that again. It's still accounted for already. And then 2. So that is our domain. So we might say x equals, and then that set of numbers. So that would be our domain in this particular situation. And then our range is all the possible values that can be outputted. So those are the y values in this case. So you would say y equals curly brace. All the values that can be outputted are -1, 0, 1, 3, 4, and -6. And we'll close the curly brace. Most of the time you want to write these in order from least to greatest, but I just wanted to kind of go ahead and get these out there and show you what the domain and range are. So again, domain is the input values. Again, the last two letters in domain are in, and so that can remind you is the input or the x values. All right, so at this time we'll take a short break from that, and let's go to this Desmos activity that you may work on your own. That's fine. You may have already done something similar to this, but I wanted to kind of walk through this with you. So just to kind of give you some examples of domain and range. So it says drag one of the blue points, so that here are our blue points here, so that fix the shaded region so that it covers the entire graph at the smallest interval. So what I need to do here is move this point here so that it just covers the graph like that. So from here to here, this point to this point make up our domain. So it's from -1, 2, 3, -3, all the way to 1, 2, 3, 4, 5, 6. So from -3 to 6, and we want to know what represents that. So only one of them has -3 and 6, but what we're saying here is x is greater, so remember these two are further apart than the one over here, so it's saying x is greater than -3, or you can say -3 is less than or equal to x, but really x is greater than or equal to -3, but less than or equal to 6. So it's sandwiched in between those two. Anytime you want to sandwich a value in between two, you always do less than on both sides, and in this case less than or equal to on both sides. And then you put the values on the outside, and that will sandwich x in between those two. So this is our domain from -3 to 6, and I'm going to say inclusive because it includes -3 and 6. And that's why it has the greater than or equal to here. Okay? So x is greater than or equal to -3. All right, let's move on to the next one. So we're going to drag the blue points to cover the graph with the least amount of shading possible. There we go. So again, the domain is from the left side to the right side. So from -3, it looks like, to 0. So from -3 to 0, then we're going to sandwich x in between -3 and 0. So that's going to be these less than signs. And then it's inclusive because it includes these 2 points. And I'll go ahead and talk a little bit about that too. This is a closed point, so that means -3 has an output value. Okay, so -3 has an output of 5. If this were an open circle, that would mean that all the way up to -3 has an output, but at that very point, -3 does not have one. So -2.999999 would have an output, but -3 would not. So that would be exclusive. Okay? So if I say exclusive, meaning it doesn't include that last one, it would not include the equal to sign. We'll see an example of that in just a bit. Okay, so again, we're going to drag here. So we're going to drag this one to the left to cover it just there. And since this has an arrow on this one, we want to go all the way as far as we can. So it's from -1 to, I stopped at 10, but realistically it's going to keep going on forever, right? So it's from -1 and onward. So for all these x values from -1 and above. So all x values greater than or equal to -1, which goes back to the bell work. We wrote it in the bell work, didn't we? All x values greater than or equal to -1. So it would be that one there. All right, up next, we have, remember this function, it's kind of a part of that periodic function we looked at in the warm-up. It's kind of, the domain is shrunk down, but anyways, let's talk about the domain here. So let's cover it just as much, little space as possible here. Okay, so we brought it to the endpoints. So it's from 1 to 6. Notice 6, there's a point, so 6 should be included. But at 1, it's an open point, meaning at 1 it should not be included. And just to the right of 1, 1.0001 or something should be, but not 1 itself. So we want to start at 1, but not include 1. So x is greater than or equal to, not equal to, just greater than 1, and less than or equal to 6. Because we want to sandwich it in between 1 and 6, but we don't want to include the left endpoint here at 1 because of that open circle. All right, the domain of this one, let's see, it's got an arrow there, so it's going to continue all the way to the right, all the way to the left, and forever both ways. So really from negative infinity all the way to positive infinity. So every value, we call that all real numbers. All real numbers are included in the domain. So one way to write that is with this like double R looking thing. That's the symbol for all real numbers. Or you could just say all real numbers and just type it in. I suppose you could do from negative infinity to infinity. We never include infinity. That's just not possible. So anytime you have infinity as one of your endpoints, then you always just do greater than or less than. You don't do equal to. All right, let's continue on here. Let's see if we can get one here that we have to type in. Okay, so this one, what is the domain of this function? So I'm going to pause for a second and see if you can do that. Okay, so if we think about all the values that can be inputted, or that are inputted, well, out here, there's no function out here. So we can't input -3 and tell what we get. It's not there. So the very first point is that -1 here and onward. So -1 has a point there. 0 does, 4, 5, 6, 7, all the way. We're going to assume it goes all the way to infinity. Does. So therefore, our domain is all x values greater than or equal to -1. So let's type that in. All x values greater than or equal to -1. All right. So, number 7. We're going to switch to range now. Again, range, similar concept, only now we're looking at the y values and not the x. So we need to cover this, but notice our 2 points here on the y-axis now. So when we think about shading the graph to determine our range, we're going to go vertically now. So we want to shade this just with as little shading as possible. Oh, there we go. And then look at what are the values in between here. All right, so it starts at a y value of 1, 2, 3, and it goes to 4. So between 1 and 4, right in here, that is our range. So we would say, not this one. This one's actually doesn't have a correct answer, so let's write it in. So it would be this, but we should say y instead of x. So 1 is less than or equal to y is less than or equal to 4. Again, we want to sandwich y in between 1 and 4. So we do the less than, in this case equal to sandwich it in between the 1 and 4. So that's our range for this one. It's all possible output values in the graph. Okay. Again, this one, we'll rather quickly through this one here. If we extend it, the range is from -4 all the way to 5. So -4 less than or equal to y is less than or equal to 5. This one there. Let's see. This one's going to go from -4 all the way. Notice the arrow, so it's going to continue going up, 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 all the way to infinity. So all y values greater than or equal to -4. Alright, this one, even though it's got the open point, we're going to go all the way to the very top of where that function goes. So what we call the maximum value of this function, if you remember. And then I'll go all the way down to the minimum value of this function. So again, bringing up those key features that we talked about in session 1. So that's from 1 to 5. Alright, these arrows indicate it's going to keep going out and up. And this is actually the cube root function is what that is. It's the cube root. Not the square root, but the cube root of x. So it's all real numbers because it extends all the way upwards and downwards. This one's going to be from 0 to infinity. By the way, this is an exponential decay function. Bring that back up again. It's going to get really, really, really close to 0, but never actually touch it. So we're going to say y is greater than 0. Y is greater than 0. It doesn't actually touch it. So if it touched it, we could say y is greater than or equal to 0, but it doesn't actually ever reach there. If you were to keep, let's say, going back to that dividing by 2 example, if you were to take a number and keep dividing it by 2, divide by 2, divide by 2, divide by 2, divide by 2, divide. You're going to get smaller and smaller numbers, but you're never actually going to reach 0. So that's the concept going on here. Oh, see if you remember this function type. Again, it's not one we deal with a whole lot in integrated math 1, but this is a quadratic function. We can still talk about the range though. So the range, again, all y values that can be outputted here. So if we think about that shading that we were doing, it would go from here all the way up. So from -2 and upward. So we're going to say all y values greater than or equal to -2. We're going to assume that actually reaches down to the -2 point here with that quadratic. Okay? It says drag the function so that the following domain and range. So domain has to be greater than or equal to -4, so we're going to bring it to the left to -4, and then it has to be range is less than or equal to 6. So right about there. There we go. So the domain is from here onward, so from -4 onward, so greater than equal to -4. And then the range is all y values less than or equal to 6. Alright, so hopefully that gave you a good introduction to domain and range from a table, graph, and a set of points. Let's also look at the last little bit of that goal that we talked about earlier was getting a reasonable domain within a context. So here we have profit along the y-axis and number of ice cream cones sold along the x. So you can see here that it's a linear function, remember that type of function there, with a constant increase. And so what we want to think about is what's a reasonable domain. So can we sell negative ice cream cones? No, right? We cannot. When we start selling ice cream cones, so like when we've sold maybe just a couple ice cream cones, our profit's still negative. We still have a negative profit, meaning we maybe owed some money to start up the company or something like that, right? And we still haven't broken even, right? We don't break even until we sell, maybe it looks like 21 or so ice cream cones. So we can sell 0 ice cream cones, right? We haven't started yet. We can sell 1, 2, 3, and so on. But selling negative ice cream cones does not make sense in this situation. So the reasonable domain for this context would be all x values greater than or equal to 0. And the same thing applies with like time. Let's say this is profit with respect to time in days or something like that. Well, we really can't talk about negative days, and so the same thing would apply there. So that's just an example of how the domain might be altered, or at least think about it differently because of the context. So if we just see this graph without any context, its domain will be all real numbers. But because of the context, we would say the domain is from 0 to infinity, or all x values greater than or equal to 0. All right, so with that, let me conclude this lesson with our goal for today, which was to identify the domain and range in various representations, as well as identify a reasonable domain for a context. So with that concludes our first unit in Integrated Math 1.